Next up, we have Farzad. He's an FPGA Computing Systems Engineer in the Computer Architecture Group in the Computer Science Department at Lawrence Berkeley National Lab. His research involves using FPGAs for design space exploration of computer architectures for scientific workflows. With that, thanks, Farzad, and you can take it from here.
Great. Thanks, Sagar. Hello, everyone. Good afternoon. I'll try to make this quick so you guys can get to your break. So I'm here to present the Berkeley eXtensible environment. It's work here we've done at Lawrence Berkeley National Lab. So just to give you sort of overview of the talk here, let's get into the motivation for like who we are and what we do. So like Sagar mentioned in the intro, I'm in the computer architecture group at Lawrence Berkeley National Lab. Our mission is to deliver deliver continued increases in performance for scientific applications through the development of open source programming, utilizing like advanced computing architectures. We deploy these workloads. We deploy anywhere within in the workload, be it at the data center, at the supercomputer, or all the way at the edge at the sensor as well. This is like sort of ranges the gamut. And we want to be able to bring these HPC tools and techniques to various application areas and try to do a lot of this through co-design. Now, a lot of this work is funded through the IARPA Agile program. Now, this is a wonderful backronym for the Advanced Graphic Intelligence Logical Computing Environment. Basically, the goal of the program is that current architectures aren't efficient enough to operate on distributed, sparse, time-varying data. And so we want to build new architectures and new ways to access these complex data streams. And this requires a fundamental rethinking of computer architectures. And we need to be able to use this information to help develop new architectures for these kinds of applications and sort of keep the performance growth with these new capabilities. The goal of the program is also to make sure that these co-designed architectures are open source as well. Open source is a very big part of what we do here at the lab. So with all that boring bureaucracy and background behind us, what are we here to talk about? Well, most of what we do here is with hardware development flows. So once you have an architect, you have to come up with an architecture that fits your specific application. You go through the design process, you go through implementation, then there's that whole process of verification and implementation going back and forth. Then you go to tape out and you go to validation. Traditionally, this is a very slow process, something you can ask any hardware engineer. My code is simulating. Basically, you got to wait for all these with traditional traditional HDLs. You'd have to like sit there, wait for your simulation to complete. Thankfully, with Chipyard and FireSim, that makes it a lot more enticing and better for these kinds of architecture explorations. So with the company behind us, what do we provide here at the lab? So we have a bunch of FPGAs, specifically a bunch of Alveo U250s and U280s. We use this FPGA cluster for hardware emulation with or without RISC-V cores. We have a many-core RISC-V implementation with a lot of where you can put in your own heterogeneous architectures. And we want to make sure that these, like, while you can do all this hardware design, you also have to make sure that it's usable for the software, for the programmers. Otherwise, you have a very nice paperweight. So we have to make sure that these support RISC-V Linux or bare metal C implementations. We also need to provide the performers in this program access to tools and to generate, and we also need to take their stuff that they give us and be able to generate it ourselves and deploy it on this hardware. And we need to make sure that this is orders of magnitudes faster than software simulation without burning the entire project budget on AWS F1 bills. So we want to be able to utilize all this hardware, this FPGA hardware that we have with the awesome simulation capabilities that FireSim provides. So talked about it in general. What is BXE? Well, it's the Berkeley Extensible Environment Cluster. This is a bare bones FPGA cluster with 48 U250s and U280s. We have these FPGAs, you get direct integration with the hardware design that you're testing over PCI Express or Ethernet. And you can, given that these are Alveo platforms, you can use a standard XRT shell, or you can use this ESNet SmartNIC shell. I'll get into a little bit more details as to what that is, but it's based on the open source OpenNIC shell that Xilinx maintains, which is supported on the U250, U50, U55, U200, as well as the U250 and 280. And the use case for this is to be able to provide users and researchers direct, no-frills hardware development access and testing to that kind of environment. So besides just access to hardware, this is also a virtual machine environment. So each performer or researcher gets assigned a virtual machine with 8 CPUs, 128 gigabytes of memory, and Ubuntu and develop for the Alveo platform. Currently, we have this running on 2 hosts. Each of these hosts has 2 terabytes of RAM and a total of 16 Alveo U250s. So I'm going to get into a little bit more details as to one of the use cases where we use it for our own research. For doing computer architecture research in this field. This is the Mosaic, an actual acronym this time, for Modular System for Accelerator Integration and Communication. This is a joint project that we did with ESNet and Xilinx. Basically, we developed this network processing area where we can inject packets into the FPGA, network packets into the FPGA, process them in real time and send them to a bunch of accelerators. And in this case, we used 32-bit Pico RISC-V processors to do some, in-network processing, and then ship it back out to the network. And so we can do some in-network processing, run some applications on this mesh network of RISC-Vs, for example. So I'll go into a little bit more details as to what the shell provides. So as I mentioned, that this is based on the ESNet SmartNIC. This is based on the AMD OpenNIC shell. All of these projects are open source and available on GitHub. What's inside the OpenNIC shell is you get this network packet unit that connects up to these QSFP cages that give you 100 gigabit Ethernet capabilities. This process at line rate, so you can send packets into this user logic block, where you can implement your own accelerator or your own custom code, running at a little bit lower frequency, but you also get you get this network stream directly into your logic. You also have a connection to the host system as well over PCI Express. The idea being that you can then do some sort of design space exploration in this user logic blocks with this, with all these extra shell bits as well. So what have we implemented for Mosaic? So we'll start out with here in the smallest component, which we call the tile or the chiplet. This is composed of a Pico RISC-V, Pico RISC-V 32. That we have added some ISA extensions, which are described here. We'll get into what these specifics are later. But we also have a mesh NOC that we've implemented. And so we can inject packets, and the core can eject packets directly into this network, this mesh network, which has switches that then connect to its corresponding neighbors. So once we have with this tile, we can then drop it into this chip package, which is this greater network. But it's not just limited to this Pico RISC-V. You can even drop in your own accelerator to utilize this network and live within this mesh network. And then you can utilize the extensions that we added. Here we have some message queue extensions that just send messages to any of the cores here on the network. And we also have these cores are also implemented in a partitioned global address space, so you can do direct PGAS extensions as well within the core to implement your application. So as a general sense, just to recap, you can have like a sea of RISC-V accelerators here, or you can drop in your own custom IP that we can then put some test drivers into the RISC-V to test out the IP blocks. And it's not just limited to one. You can drop in multiple IP blocks. We also have system calls to the Linux hosts to be able to better communicate with these RISC-V cores in this mesh network. So the current status of this Mosaic framework is that we have all this implemented in Verilog. We've also modified the ESNet SmartNIC OpenNIC shell to add a DDR memory controller. And we have some configurable cache dimensions that connect up to this mesh network. And we have this all running in simulation currently. And we also have we're currently working to deploy this with this new packet generator that we have. A lot of this is written in Python, but basically this you can generate traffic to inject into this NOC to test out whatever you're testing in this mesh network. All this, like I mentioned, this FPGA hardware is deployed, and we're validating all the memory controller, and that's the current status. In the future, we'd like to port this, given that this was all written with in Verilog and we'd like to port this to Chipyard through a ROC extension and utilize the newly released Constellation to implement our NOC explorations. So the whole reason why we're here is we're also doing some work to integrate FireSim with BXE. So how hard is it? Well, given that our environment supports the standard Xilinx tool set, we have support for the XRT shell. FireSim has documentation on how to do an on-premises install with the XRT shell. So what's the holdup? Well, nothing really. It's fairly straightforward if you follow the documentation. We are 99% there. We are almost booting Linux. The entire FireSim environment builds within our virtual machines. There's currently a bug with our board XRT version. Any of you who've worked with the U250 are very familiar with how finicky XRT can be. But it's fairly straightforward. You can now, FireSim has thankfully published all the documentation on how to do this yourselves, and also how to import your own designs into FireSim. In the future, so when we do resolve our XRT bugs, we do plan on bringing the FireSim shell within ESNet. We'd like to be able to use enable the ability to use the memory controller on these within this shell. And we'd also love to be able to provide support for the network processing unit to be able to do some interesting network experiments with your FireSim design. So in conclusion, talked about BXE. It's a VM-based FPGA environment for hardware design. We're currently working on integrating this with FireSim, working closely with the FireSim team also. Thank you for all the support. We also presented some of the work we've done with Mosaic to do component testing of different IP blocks within an FPGA. I'd also like to thank the FireSim Chipyard team for all their work in building up this FireSim Chipyard environment. And thank you very much for putting on this wonderful workshop that we can share all this work and be able to work with all these other people who are doing excellent work. I'm happy to take any questions.
All right, awesome. Thanks for that. Any questions? Yeah.
Can you hear me?
Oh, maybe you can come up here.
Yeah.
Wasn't sure about AV setup.
Yeah.
No
Yeah,
worries.
we had to roll our own AV setup. Yeah, it's bare bones.
Hi, can you hear me?
Yes.
Yeah, very interesting talk. I was wondering, I asked that question already yesterday, but since you have the same hardware we have you attempted to migrate FireSim to the U280 instead of the U250?
We have a U280. We just haven't gotten around to it yet. We have a lot more U250s, and the U280, unfortunately, is used a lot in a lot of other experiments. But the U280 is also on the roadmap.
It's also on the roadmap. Okay, so we are going to try that as well. In case we manage to get it up and running, I might send you an email.
Looking forward to it. We'd love to work with you guys.
Okay, thanks.
Hey, Farzad, when you mentioned that the thing is almost booting Linux, do you mean that the target isn't able to boot Linux at the moment?
Essentially, we couldn't program the board. It's an XRT issue. Abe sent us a link on how to fix it, and right before Abe sent that, one of my colleagues sent me a link to the kernel error we were seeing. Essentially, what stopped us was that I lost power in the PG&E storms, and that was exactly when I found this bug. So I haven't gotten around to fix it yet.
Thanks.
Good question.
So you have a lot of FPGAs. Are you looking to make your cluster environment open source to potentially people outside of LBL, or is this strictly an LBL specific infrastructure? And if so, if it's specific to LBL, do you have any open source plans for some of this infrastructure?
Yeah, ideally, we'd like to have this be a facility that other people besides us can just use, much like how NERSC is provided as like a supercomputing center where people can apply to use the supercomputer. We'd like to be able to do the same thing for this FPGA infrastructure as well. And so, yeah, it is planning on being open source, and we're happy to share how the setup process with others who'd like to bring it up on their own premises.
So I guess to poke a little bit here, is there a timeline for potentially having like applications open for people external to LBL to use this infrastructure?
That would be a great question. Unfortunately, I don't have any specific dates as to when this will be available. But I will say, like, within definitely the next year or so.
Okay, thank you.
Any other questions? So I have a quick question. So you mentioned integrating the networking infrastructure that's on these FPGAs. Have you done any measurements of like what kind of latency you get trying to get off the FPGA or between multiple FPGAs yet?
I don't have those numbers on me right now. I will say that this ESNet SmartNIC is part of the ESNet 6 deployment. So this is currently being used in the field to do in situ network processing, network packet processing, and latency is something that is a very big issue for them. So I can't imagine there's much of a latency going through this, but I unfortunately I don't have any specifics as to what they are.
Okay. Cool, awesome. Any final questions? All right, thanks Farzad again.
Thank you, everybody.
We'll